Good morning or good afternoon, as the case may be. My name is Sosale Mohana. I'm a maths teacher who has taught maths for over 50 years in 3 continents and 3 countries, like India, in Asia, Kenya in Africa, and England in Europe. I've just retired a couple of years ago, and I thought I should use my experience to record and deliver a number of lessons based on the British curriculum for A-level maths, so the students who want to reinforce their learning can use it. I have a master's in maths, of course, way back in 1969. I completed my master's in maths, and then I did my teacher training in 1974. I've been working since 1969 till 2019, clear 50 years. So I hope these lessons are useful to you, and you're welcome to watch them. And then with each lesson, there will always be a document which covers whatever has been done in the lesson. So you could use that perhaps as your own notes, or maybe to go over what has been taught during the lesson. I hope you enjoy the lesson. Hello, everyone. This is the third lesson on the history of quadratic. I thought, instead of giving you one whole boring story, I'd give you three, one longish, short, and short, three boring stories instead of one. So that, those who are not interested in all these stories can skip and go directly to solving quadratic equations the way we teach in class. But I thought I find it very exciting and interesting. I hope you do too. So in the last lesson, I traced the link from x squared equal to 2 or x equal to root 2 way back in 350 BC to the paper sizes, excuse me, A0, A1, A2, A3 up to, of 1857, which is today's standard paper sizes used everywhere in the world. Fine. So as I raised a question, so we're just talking of only root 2. What's so great? It's fine. We accept root 2 are the very first one down. It is useful. But then why can't we get on with quadratic? That's not the only one. Hang on. So to do that, today I'm going to take something which is more interesting than that. In other words, you remember the American Foolscap. And quadratics. How quadratic equations influence every bit of our life. American Foolscap and the quadratics. Now, how do we understand this? This is an example of a Foolscap. This could be A4. I didn't bring a Foolscap. Sorry, I didn't have one. So I'm using this just to illustrate. Let's assume, let me write it here. This length is 1 and that width is x. Can you see that? Let me bring it a bit closer so that you can see. So the length is 1, the width is x. So if I were to fold this, remember you used to make boats when you were young in the rainy season to put them in the stream. We used to do it in India. Obviously, every child will have done it some stage or the other, making a boat and putting it in the water. All of you have done it. Now look, I have folded like this so that this width x has gone into this. So now can you see this remaining paper? This remaining paper is, the total length was 1. I have removed x, so I'm left with 1 minus x. So the Foolscap, I'm assuming, has length 1 and x. It's easier that way. When you stick one side as 1, the ratio becomes easier to work with. And then I folded this so that I now got a rectangle. That was 1 minus x and that was x. And obviously I need to turn it round. So I will rotate it. So that will become x and 1 minus x. Okay? Remember, the ratio, my job is to find what is x. The ratios must be the same because the same concept applies as it happened in A0, A1, A2, A3, A4. The two must be similar. That's the condition for an A4 paper or for a Foolscap. So what the ratio here? X over 1. What the ratio there? 1 minus x. Oh, sorry. That is 1 minus x. That is x. So that ratio is 1 minus x over x. So the ratios must be the same. X over 1 equal to 1 minus x over x. Cross multiply, you get x squared equal to 1 minus x. So x squared minus plus x minus 1 equal to 0. That's the next quadratic which people trying to design the Foolscap came up with. And you know how to solve a quadratic equation. You have been learning minus b plus minus root. So therefore what you did was x squared plus x minus 1 equal to 0. I'm trying to find the dimensions of a Foolscap. So they said a is 1, b is 1, c is minus 1, and then you did minus b plus minus root b squared minus 4ac whole over 2a. Big formula, you applied everything, and then you got x to be minus 1. Okay, let's write the formula. Minus 1 plus minus root of 1 minus 4 times 1 times minus 1 whole over 2, which is minus 1 plus or minus root 5 over 2. So they said x equal to minus 1 plus root 5, which is root 5 minus 1. But I don't use the other one because minus 1 minus root 5 over 2 I'm not going to use because it's going to be negative and the length of the side cannot be negative. Let's evaluate this answer. This answer is 0.61803. Blah, 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 blah. Okay? But then, where did this lead to? This particular answer, root 5 minus 1 over 2, is given a special Greek name called phi, which is the golden ratio. That means it is the most aesthetic ratio. If you take up a modern day portrait, if you take the width and the length, for it to be most pleasing and for it to bring out the whole effect of the picture within the frame should have as close as possible the golden ratio. That means if you take the width of the frame and if you divide by the length of the frame, it should be 0.61803. This is being used in photographs, the various size photographs you get, in portraits. And this is not now. In the Georgian times, you have Georgian architecture, lovely Georgian windows. If you go back to a building which was built in Georgian style, and if you measure the width and if you measure the length, divide the width by the length, you will get somewhere around 0.618 or 0.62. That's again the golden ratio. Fine. So why is that very important? See, because one of the most beautiful architectures is the Georgian architecture. It's pleasing to the eye and it brings out the proportion well. It looks well presented. That's why it's called the golden ratio. But to understand this, we need to move forward or move back, as the case may be. I can't remember when the gentleman was, I think even the 1700s, if I'm correct. Let's look at something else. Let's look at a sequence of numbers 1 and 1. I sorted two numbers. After the second number, what I'm going to use is every number is the sum of the numbers, two numbers behind it. So the third number is 1 plus 1, 2. The fourth number is previous to 2 plus 1, 3. The fifth number is 3 plus 2, 5. Sixth number is 5 plus 3, 8. Seventh number is 8 plus 5, 13. Eighth number is 13 plus 8, 21, and so on and so on and so on. This is called a Fibonacci sequence. A Fibonacci sequence. It was first discovered by a mathematician called Fibonacci, and he was trying to predict the way rabbits multiply. So he came up with that section. Second, two rabbits, 2, and then the next one will be 3, then the next generation 5, next generation 8. That's how the rabbit population multiplies itself so quickly. He came up with that. But then it's a very, very important sequence because it's found in abundance in nature. One of the examples would be if you were to count, let's say there's a plant. Start with the bottom stalk, number of leaves, next stalk, number of leaves, second, third stalk, fourth stalk, and so on. If you take a number of plants of the same species and try to make a table, the numbers follow members of the Fibonacci sequence. Also, if you take up a pineapple, the small round things around in a pineapple, the ridges, they're called the eyes. If you take about 10, 12 pineapples and then count the number of eyes, you'll see that number of eyes is a part of the Fibonacci sequence. And if you were to see the number of circular seeds in the circular holes of a sunflower, they follow Fibonacci sequence. And nature is something which does not do anything without a purpose. You have learned from your biology lessons, for everything in nature there is a purpose, including a microorganism to the biggest animal you can think of in the world. There is a purpose. You may not accept what the purpose, agree with the purpose, but the purpose is there. And therefore, generally, since this is found in abundance in nature, scientists are still investigating what could be the link between a Fibonacci number and what's happening in life. Anyway, coming back to this, one thing very important. Suppose I call this as U0, U1, U2, U3, U4, U5, U6, U7, etc. U0 over U1 is 1. U1 over U2 is half. U2 over U3 is 2/3, which is 0.67. U3 over U4 is 3 over 5, which is 0.6. U5 over U6 is U0 over U1, U1 over U2 is half, U2 over U3 is 2 over 3, U3 over U4 is 3 over 5. I should have done U4 over U5, sorry. U4 over U5 is 5 over 8, which is 0.625. Then, is that? Yeah. U5 over U6 is 8 over 13. And that I have worked out somewhere is 0.6158. And then, suppose you do U6 over U7. I did work that out. So let me work that out. U6 over U7, that is 13 divided by 21. 0.619. What the next number? 21 plus 10, 31 plus 3, 34, right? Because U8 will be the sum of the previous two. So just out of interest, 21 over 34 is 0.6176. And then 34 plus 20, 54 plus 1, 55. So 34 divided by 55, 0.618. So if you find the next two ratios, I get 0.618, 0.618, 09. Can you see that there? In other words, the ratio of successive terms of a Fibonacci sequence leads to the golden ratio. And golden ratio is the most aesthetic ratio, most pleasing ratio. And that is nothing but square the root of a quadratic, which we learned how to solve, which we reduced from A4. That is why A4 paper is considered to be very aesthetic. That's how standard size they use. It's the most comfortable to write on. So you can see quadratic equations have umpteen uses. As I said, these three lessons, this one, the previous two, are only more about history and stories. So you won't have any handouts or notes. It's just to make the topic more interesting than just starting with ax squared plus bx plus c equals. This is a quadratic, this is how you solve, this is how you factorize, this is discriminant, blah, blah, blah. So now the story time is over. We're back to maths. In the next lesson, I will talk to you more about how to solve a quadratic equation, its applications, then inequalities, and so on and so on and so on. Thank you very much. Hello. I want to take this opportunity to propose a vote of thanks. I would like to thank Vivid Innovations Private Limited and Commerce Forum for so generously giving up their studio and the facilities and the services of their technicians to record all these videos for free. I think that needs to be acknowledged and appreciated. Thank you very much. And my special thanks to Mr. Nitin Mahadevappa, Mr. Nishant Guruswamy, and Mr. Sadan Kumar DN for all their help and assistance in getting these videos ready, uploaded, and launched. Thank you very much.